Hello, and welcome to Aggressive Physics. Today is day 126, and what I'd like to do today is discuss magnetic fields. Now, around every magnet exists a magnetic field, and that's the force that a magnet will exert on other objects. It exists with an inverse square law, just like many of the other forces that we've discussed in this course. In fact, if I double the distance away from a magnet, I'm going to decrease the force that that magnet exerts by 1/4. So if I triple the distance, it's 1/9. If I quadruple the distance away, it will be 1/16. So it's an inverse square relationship. Now we can draw magnetic fields around magnets in a similar way than that we did when we did electric fields. And the way we do that is we draw lines of flux. Now there's a few rules to drawing lines of flux. First of all, they always form closed loops. And unlike electric fields that stopped when you got to the surface of the metal conductor, the magnetic field exists inside the magnet. So when we draw the magnetic fields around a bar magnet, or we try to simulate the magnetic fields around the Earth's surface, what we'll see is that the magnetic field lines do continue into the circle of the Earth, or into the usually rectangular structure of the bar magnet itself. The magnetic field is always stronger where the lines are closer together. So the magnetic field strength in the magnet is stronger than at the surface. And as we move farther from the magnet, you'll see that the lines spread out and they're farther apart. Now that's very similar to topographical lines, just like we talked about when we discussed electric fields. In addition, the direction that we choose is from north to south. So our convention is similar to the electric fields. With the electric fields, it was what would a proton do, WWPD. With magnetic fields, it's WWNPD. What would the North Pole do? Finally, the number of field lines represents the strength of the field. So if we have a much stronger magnetic field, we're going to draw more lines of flux around the field. The direction of the field itself will be tangent to the field lines. So if I were to figure out the direction of the force, I would have that acting perpendicular to the lines. That's a little different than the electric field, which was parallel to the electric field lines themselves. Now, when we take the whiteboard out in a little while, what we're going to do is simulate what the magnetic fields look like for a number of different shapes and a number of different types of magnets. So magnetic field lines and electric field lines are something that you'll be responsible for knowing about when you take assessments. As far as the magnetic field strength, what we do is we measure the flux density. And the flux density is the number of field lines that exist in a given area. Now the flux density is measured in Teslas, and the symbol we use is the B. B is the variable for the magnetic field strength, and T is the unit. So T is for Tesla, and it's named in honor of Nicholas Tesla. For example, in terms of field strength, the Earth's magnetic field, as I stated in an earlier video, is around 5 × 10⁻⁵ Tesla, whereas an MRI, a magnetic resonance imaging machine, is around 1 Tesla. So the strength of an MRI is much stronger than the Earth's magnetic field. And that's why it's important that if you ever go into an MRI, that you need to remove all metallic objects from you. They can be easily pulled into the machine, and if it flies into the machine, it could do a lot of damage to the machine and also injure you when you're in the MRI itself. Now, since the field strength is perpendicular, or the force is perpendicular to the field lines, the lines of flux that we draw, what we have is a situation where the maximum force is going to be perpendicular. You can have forces exist when you have an angled field line, but it's always going to be the strongest when it's perpendicular. So that will allow us to maximize the force by producing a perpendicular to the line of flux. What we'll be able to do with that is actually determine the direction of magnetic fields using what we call right-hand rules, and realizing that they're always going to be strongest when they're perpendicular. If they're not perpendicular, what you would have to do is know the angle at which the field is compared to the object at question, find the value of the perpendicular, and then use that in your equation. And we'll do a little bit of that later. But for now, if we realize that magnetic fields can be drawn, and the lines are called lines of flux, the unit for magnetic field strength is the Tesla, and the symbol is the B, what we'll be able to do is take the whiteboard out and draw some sample magnetic field lines at this point. So for today, I want you to get a visual representation of the magnetic field and realize that where you have the lines closer together, it's stronger. Where they're spread out, it's weaker. And one of the big differences between this and electric fields is that magnetic fields exist inside the magnet, and they're going to be really close together in the magnet, so it's stronger actually inside the magnet. So magnetic field strength exists within the magnet itself. Outside the magnet, it will still exist, and we can see that when we affect other objects, when we bring magnets near them. But the most important thing is also that the perpendicular is going to produce the strongest force. So let's take out the whiteboard now and look at some visual representations of the magnetic fields. Thank you. All right, just like electric fields, what we can have is a visual representation of magnetic fields. And the rules are similar. But instead of going from positive to negative, we go from North Pole to South Pole. And one of the major differences with a magnetic field is that it exists within the structure of the magnet itself. So the field lines do exist inside. We're not going to be able to show them because we can't get, in this case, we're not going to be able to get a compass to go inside the magnet. But that's the major difference between magnetic fields and electric fields. The electric field, as you remember, there's no field inside of the conductor. But in this case, there is a field inside the magnet. So that's why when we put the piece of metal in the electromagnet, which the fancy term is the solenoid, we'll find that it makes it stronger, because that is acting as a conduit for forcing the field lines closer together, which makes a stronger field. So very similar to contour lines, but what we can do is visually represent it. All we need is a magnet and a compass. And sometimes compasses become magnetized with the opposite pole if they're near strong magnets. So I would not suggest using a compass that's something that you use perhaps for navigation in the woods. Use a cheaper compass that you're not going to use to have your life depend upon it, because it could actually switch the poles. Now, if you take this, and you'll notice that the red is pointing to the south, and this is going to line up within the field. What you can do is you can put a dot near, in this case, I have a compass that has a red and a white, so the red is north and the white is south. And then you can move the red line to where the dot was. Make another dot at the white. Move the red line, make another dot. Move the red line, make another dot. And right about there. And what we'll find is that the field will wrap around. And if you keep putting dots at the white, what you'll see is that that follows the magnetic field line. And if we connect the dots, get out of my way, compass. You just drew a magnetic field line, and we label it from north to south. Now, if we go a little closer here, we'll see that if I mark the red, and the red, we have a little smaller line here. Still goes from north to south. And if we go in between the spot we did before, the North Pole is going to track that compass needle little too strong, right about there, and you get a line like this. So it goes from north to south. Now, just to make it symmetrical, I'll go here, and we'll see if we can map the field beneath. It should be just about symmetric, but I have a lot of magnets on my table, so some of those may be affecting the results. And we do this as a lab in class, and every year I have students getting results that are odd, mainly because they have either, whoop, that wasn't very smooth. They either have their partner's magnet really close to them, north to south, this way, or they have another magnet that they may be using later right next to their magnet. So they may have another magnet here, and all of a sudden their field, it's not affecting the field correctly because the magnet's too close. You got to bring it further away. So other magnetic fields will affect the way the field looks. Now, if you trace the original magnet and you label the north and south, this shows, very similar to what we did in the lecture, what a visual representation of a bar magnet is. And if we rotate it 90 degrees, that's similar to how the Earth's magnetic field works. The Earth acts as a big bar magnet. So that's how we do a single magnet and a single bar magnet. Let's look at another one now. All right, let's map the field in between two unlike poles that are a number of inches apart. Now I'm going to mark, in this case, the white spot and just trace to see where it ends up. And what this will do is look very similar to what we did in the lecture portion. That's going to connect right there. So there's one line, like that, north to south. Let's do one directly in the middle. One. And all you have to do is just mark where the compass points, line up the one that was closer to the magnet with the dot that you made, and then mark a new dot where it's pointing. And the compass lines up within the magnetic field. Something like that. And it's not going to be perfect. Some magnets, one may be stronger than the other, and it may be because we have a situation where one of the magnets was damaged, perhaps. But generally, this is the shape we're going to get. Of course, on the assessments, they'll typically use ideal situations, so you'll have fields that look much more symmetric than in reality, but we've noticed that in lab as well. So we do one there, and then maybe we'll do one down here and see if it may not even connect. It may not be strong enough to pull this north pole to the other side. Well, it doesn't look like it's going to do that. Now, what's going to happen here, you're going to see that the south pole of this magnet is stronger than the south pole of the magnet on the other side. So what it actually did is it made a field line that looks like the original bar magnet. So if you're looking at in between, you'd want to stay away from ones that connect back to itself. So you'd want to maybe do one, let's say in this spot, and we'll see the symmetry once again. But this is showing me that one of the fields is a little stronger than the other. So one of these magnets, although they look identical, magnetically they're not exactly the same. And I see this curve here, and then it's not symmetric, so the stronger end is over here. So that's how you do a north and a south pole separated by a number of inches, maybe about 6 inches. All right, in this case we have two like poles. I chose north, and what we'll do is we'll see how they interact in the middle. Now I'm going to line up, and the compass is fighting the other magnet's field. And we'll see that it's going to start turning back onto itself, and it probably won't connect again. So we have this turn here away. That was very similar to two like charges when we did electric fields. Let's see. Oh, look at that. Also repelling. So we have field that goes like this. And we'll try one on this side. We'll just do 4 to see the symmetry. 2, 3 dots. And this is something that I have my students do in lab as well, just to get a nice visual representation of the field. And it's very easy to do. If you have a compass and even a kitchen magnet right now, you can do this at home. You don't have to wait for lab. You can have all the fun now and then have more fun when we do it in the lab. Now you'll notice I'm drawing the arrows away from the north. I just happen to do 2 north poles. If they were south poles, they would be the other direction. Now if I go directly in the center, what we'll see is that there will be possibly a flip at one point. No, curve's good. Looking good. We have that. We have a curve. And then we'll try one down here. And I did move the magnet, so that may have affected some of the results. One there. One there. One there. And then a quick turn. And then what we have in the center is this area where they are effectively battling. So the field looks like this. And if we look, there should be a spot directly in the middle where there's no field because the 2 fields are opposing each other. And this is your asymptote. So these would approach that and never actually touch it. So we have this opposing forces with the magnetic fields like this. So that's 2 like poles, similar poles.